All right, today we're jumping into something pretty incredible from NVIDIA called FFN Fusion. It's a new technique that could seriously change how we build and run the massive AI models that are, reshaping our world. So how on earth does it work? Let's get into it. So let's just start with a big question, a what-if scenario. What if the most powerful AI models could spit out answers almost twice as fast as they do now, while costing 35 times less for every single word they generate? I mean, it sounds a little too good to be true, right? But that is the exact promise of the technique we're going to unpack today.
Now, to really get why this is such a game changer, we first have to talk about the huge problem FFN Fusion was designed to solve, and that's AI's great computational bottleneck.
Large language models, or LLMs, they're not just some science experiment anymore. They have totally exploded out of the lab. They've become these essential tools that power everything, from the virtual assistant on your phone to honest-to-goodness breakthroughs in scientific research. They are, quite simply, everywhere.
But here's the catch. For years, the main playbook for making these models smarter was just to make them bigger, scaling them up to hundreds of billions of parameters. And sure, that's unlocked some amazing abilities, but it's also created this massive bottleneck. The cost, the sheer resources you need to run these giants, it severely limits who can even get in the game to build and improve upon them.
So, how do you break that cycle? The one where bigger means better, but it also means way, way more expensive? Well, the researchers behind FFN Fusion found a way by challenging a really core assumption about how these models are built. I like to think of it as completely rethinking the AI assembly line.
Just picture a standard LLM like this long, kind of old-school assembly line. It's made up of dozens, sometimes hundreds of these processing blocks. Information goes in one end and it has to get stamped and processed at every single station, one after the other, before an answer finally comes out at the very end. It works, but man, is it slow.
Now, a really key station on this assembly line is called the Feed-Forward Network, or FFN. And here's the super important detail you need to know. An FFN processes each token, think of it as each word, all by itself, independently. And that independence is a huge hint that maybe, just maybe, not everything has to happen one after another.
And this brings us to this huge aha moment in the research. It turns out LLMs have a lot of what's called structural redundancy. Researchers found that these key parts, called attention layers, the components that figure out how different words in a sentence relate to each other, well, a lot of them can just be removed, and it barely impacts the model's performance at all. So once those are gone, you're left with these long, uninterrupted chains of FFN layers, just sitting there waiting to be optimized.
So that discovery, that's what really sets the stage for the breakthrough. It's what unlocks the true power of FFN Fusion.
Okay, so here's how it actually works. It's basically a two-step process. First, in step one, an algorithm like Puzzle goes through the model and very strategically snips out those redundant attention layers we just talked about. That leaves you with these long back-to-back sequences of FFNs. And then comes step two, FFN Fusion.
So before the fusion happens, you've still got that long assembly line. Even with the attention layers gone, the data still has to trudge through FFN layer 66, and then 67, and then 68, and on and on. It's still a one-by-one kind of deal.
But after FFN Fusion, whoa, everything changes. The technique basically uses math to combine all those sequential layers into one single, much wider super layer. The assembly line is gone. Now it's one massive workstation where all the jobs get done at the same time in parallel. It's the same amount of work, but it gets done in a fraction of the time.
Okay, this all sounds amazing in theory, right? But does it actually work in practice? Let's dive into the case study of what they called the Ultra model to see the real-world results.
So, the researchers took an absolute beast of a model, Llama 3.1, with 405 billion parameters, and they applied this technique to it. And what came out the other side was a brand new model, Ultra 253B-base.
And the results are honestly staggering. First, let's talk speed. The new model generates responses 1.71 times faster. That's a huge leap in responsiveness.
Then you look at the cost, and this is just incredible. It is 35 times cheaper for every single token it produces. 35 times.
And it does all of this while being a mind-boggling 152 billion parameters lighter than the original. So it's faster, it's cheaper, and it's smaller. But was it still as smart?
Right, that's the crucial question. Did they have to sacrifice intelligence for all this crazy efficiency? And the answer is a resounding no. In fact, and you gotta get this, it actually got smarter. On Arena Hard, which is a really tough reasoning benchmark, the new Ultra model beats its massive parent by 12 points, and it pulls ahead on other key tests too. It's not just smaller, faster, and cheaper, it's actually better.
I mean, this is a truly remarkable result. So you have to ask yourself, where does research like this lead us? Let's take a quick look at what comes next.
Well, this research opens up so many exciting new doors. For one, by seeing which layers can be fused together, we might get a better understanding of how these AI brains actually work. It could also inspire completely new AI models that are designed for this kind of parallelism from the ground up. And you could combine this with other efficiency tricks, like mixture of experts, for maybe even bigger gains.
And maybe the most exciting hint of what's to come is this quote right from the paper. The researchers found early signs that it might be possible to parallelize not just the FFNs, but the entire transformer blocks, attention layers and all. That suggests that FFN fusion isn't the end of the story. It's just the first step in a much, much bigger revolution in how we design AI.
So, let's end with this final thought. We've seen the AI's brain basically go from a slow, step-by-step assembly line to a massive parallel workstation. If this is just the beginning of that shift, what new frontiers are we going to unlock when state-of-the-art intelligence isn't a bottleneck anymore, but is instead fast, cheap, and accessible to absolutely everyone? Thanks for tuning in.